Hey guys, I'm Dr. Low. We meet again in Chapter 4, the half-range Fourier series. Now we look at question 1. Determine the half-range sine series expansion for the function fx equal to 1, valid for the given range. Then you are asked to sketch the graphs of both fx and the periodic function represented by the series expansion for negative 3 pi to 3 pi. The half-range sine series function is given by the formula In this question, the p-value is the range of pi. So n pi x over pi gives us sine nx. Now we need to find out what is the value of Bn. By formula, the Bn is given by 2 over p integration 0 to pi, because this question range from 0 to pi, fx sine n pi x over p dx. So substituting all the values known, fx given by the question equals to 1, so 1 of sine nx. Then normal integration. We'll summarize from here. We have learned that cos n pi is governed by the value of n, whether n is odd or even. So when n is odd, say for example 1, 3, 5, so take the simplest when n is 1. So cos 1 pi gives us the value of -1. When n is 3, again odd number, we get a -1. So this is differentiated by whether the n value is even or odd. When n has a value of even number, say for example 2, cos of 2 pi is 1. So by summary, we write this as negative 1 to the power of n. So when n has the number of odd 135, we get the value of negative 1. When n takes the number of even, we get positive 1. Okay, cos 0 gives a value of 1. So calculation from here, take for n even, we get the value of 1 minus 1, so 0. When n is odd, we get negative 2. So multiply by the number outside. Now we get the values of Bn. These are the values for Bn. So the question requires a function, a Fourier series function. So substituting into the formula, Bn sine nx. So Bn takes two values. When it is even, when the n is even number, the Bn is 0, so the entire function is 0. So we left with values when n is odd. So when n is odd, we can simplify the equation, putting numbers outside the summation sign. You may leave your answer in this form, or there is another form of representing the answer. If n starts with 1 to infinity, so to get odd numbers, so you may try substituting. When n equals to 1, we have sine 1x. When n equals to 2, we have sine 3x. So 1, 3, 5, and so on. This pattern comes from the arithmetic progression. You are also asked to sketch the graphs of both fx and the periodic function. So this is just a simple sketch. From negative 3 pi to 3 pi. The function given is equal to 1 for 0 to pi. So 0 to pi gives a value of 1. So how about the remaining values of x? Half-range sine series. We know that sine series is an odd function. So when it is reflected on the y-axis, it is symmetrical at the origin. So it is supposed to be this way. So continue the same pattern. A periodic function. So that is for the graph sketching. Number 2. Determine the half-range cosine series expansion. Function given fx equal to 2x minus 1. The range given from 0 to 1. Then you are asked to sketch the graphs of both fx and the periodic function represented by the series expansion for the range from negative 2 to 2. Half-range cosine series formula given by So we need the values of A0 and AN. The formula for A0 integration 0 to 1 as given in the function the fx function So calculation from here gives the value of 0. So meaning that there's no A0 over 2. The entire term here will be 0. Now we find the value of AN. Given by the formula 2 over P integral 0 to 1, follow the range given in the question. Substituting the value of P, fx given in the question, so it looks like this integration requires integration by part. Substituting the values in the first term returns the value of 0. As learned in the previous question, cos n pi returns the value of -1 to the power of n. It depends on the value of n whether it is an even number or an odd number. So summarize from here, we get two values for an. When n is even, we get 1 minus 1, meaning 0. And when n is odd, we have -2 here. So -2 multiplied by 4, we get -8 over n pi square. So these are the values for an. When n is odd only. When n is even, the entire function is 0. So we need to replace this as odd. Or another way of writing the solution is we can pull out the values. Don't forget that we need to sketch the graphs as required by the question. This is a straight line equation. For the range from 0 to 1, so we just need 2 points. When x 0, we get the value of -1. When x is 1, we get the value of 1. Now we can sketch the pattern. To extend this graph, this is the range of cosine series. So we know that cosine is an even function. So we need to reflect symmetrical to the y-axis. For this question, a function fx is defined by the range 0 to pi in the form of piecewise functions. Find a half-range Fourier sine series expansion on this interval. Then sketch a graph of a function represented by the series for the range negative 2 pi to 2 pi. The formula for half-range Fourier sine series is given by In this case, the period for the half-range function is from 0 to pi, so it's only pi. Now we need to find the Bn. Integration of 0 to pi given by the question. we have the piecewise fx function from 0 to half pi to pi. So we break down the integral. We make use of the trigonometry formula. This part comes from the trigonometry formula sine A sine B. So continuation from here. In this case, we notice that n cannot be 1. Because once n equals to 1, we get undefined value. The integration workings are a little bit lengthy. We make use of another trigonometry formula at this point to summarize the expressions in the bracket. So from here we have this is for the first term of the previous expression. Here we can simplify the expression by calculating the values. Cos pi over 2 gives a value of 0. So this whole expression will become 0. Sine pi over 2 gives the value of 1. Cos pi over 2, 0. Sine pi over 2, 1. So substituting the values known, we will get a very much summarized form. So calculation from here. where n cannot be 1 to avoid getting undefined expression. Remember, cost values are governed by whether n is odd value or n is even value. So in this case, we can summarize the set of expressions possible for Bn. When n takes the value of odd numbers 1, 3, 5 and so on, we have cos pi over 2, cos 3 pi over 2 and so on. That gives the value of 0. When n takes the value of 2, we get cos pi. When it takes the value of 6, we get cos 3 pi. So cos pi, cos 3 pi and so on, we get the value of negative 1 here. So the entire expression will become positive. When n equals to 2, 6, 10 and so on. There is another possibility when we get the value of negative. When n equals to 4, we get cos of 2 pi. Cos of 2 pi returns the value of positive 1. Positive 1 multiplied with the negative expression, so we get negative value. So for the case of when n equals to 4, same for when n equals to 8, when n equals to 12 and so on. So it's a multiple of 4. But what happens to the case of n equals to 1? This expression only valid for n not equals to 1. What about when n equals to 1? What happens to the Bn? So what we do is, this is a special case. Bn comes from the formula of integration. So when n equals to 1, it is the same as 2 over pi, integrate from 0 to pi over 2 sine x sine nx. So your n is 1. So another sine x. To integrate sine square dx, we can make use of the formula, trigo formula. So based on this formula, so B1 returns the value of 1 over 2. So we have a range of values for Bn. Collecting all the values for Bn into the formula for the Fourier sine series, so we start from the value of B1 sine 1x. Summarizing the values of Bn we obtained in the previous steps. We have obtained the value of B1 in the earlier stage. So here we have half sine x followed by when n equals to 2 and so on. To get n equals to 2, we have the multiple of 2n here. So we get sine 2x, sine 4x and so on. After all the latency workings, we are at a point to sketch a graph for the function represented by the series from negative 2 pi to 2 pi. From the function given, 0 to half pi, the function is sine x. So 0 to half pi. Sine 0, the value 0. Sine half is 1. So it looks like this. Then we have from half pi to pi is a 0. Sine series expansion. This is an odd function. So we extend to symmetrical at the origin. So the same pattern will repeat. Question 4 is a very direct question. You are asked to represent fx, a piecewise function, in a Fourier sine and cosine series. So there are two parts. To expand in a Fourier sine and cosine series. For the Fourier sine series, the formula is here the p-value is 1. So n pi x, bn sine n pi x. So we can simplify this. So we need to find the bn. 2 over p. The p value is 1. The range is 1. 0 to half, we have fx equals to 1. So 1 sine n pi x plus the range of 0, half to 1 is 0. Zero of sine n pi x dx. So there is nothing here. So integration from here. So substituting the Bn value into the formula, the Fourier series sine expression is given by we need to pull in the n over here because it is from the value of 1 to infinity. Then we look at Fourier cosine series. The formula given by an cos n pi x over the p value. The p here is 1. So cos n pi x. So obviously we need to find the a0 and an. So this is simple. 2 over p-value, integration of 0 to half fx gives a value of 1 dx, plus the other portion is 0, so we can omit. And calculation from here gives the value of 1. Okay, then the an. Fx cos n pi x, n pi x over p, but the value of p is equal to 1, so we can omit. So integration from here. Minus sine 0, so this is 0. So what we have is putting all this information into the Fourier cosine series. The value of an we can pull out the values to summarize the second expression. Thanks for watching. Drop a like, leave a comment, and don't forget to subscribe.